Good afternoon, my dear students. So today we're going to get started to work with something which is really interesting that goes next to what we studied previous class in terms for this energy. What you're going to do, for example, for this exercise, there's two questions which are really important to take into account. That says, first of all, for the following reaction, you're supposed to find the enthalpy, which you know clearly how to do. And after this, find the change of energy, which is the class for today. Now in the enthalpy, that's pretty easy to do. So in the first place, what you will have to do is first of all, balance the reaction, right? If you check the reaction in here, it says there, have hydrogen, sodium. Yeah, I have two hydrogens there, but one oxygen. So what you must put then in here, some two. If you put a two there, then you're going to have two sodiums, two hydrogens, two oxygens, and two hydrogens plus two hydrogens is four. And then you will need to put in here also a two. So then you have two oxygens and also four hydrogens, but also two sodiums. So then two sodiums. Then after having that, that's balanced. So for finding this enthalpy, that's pretty easy to do because the only thing you would need to do is just finding delta, okay? So for doing so, you will need to just type like this symbol. Let me find it on the internet, the symbol for delta. Delta symbol. Yes, once you have it, you copy it because that's I'm using for this text stuff. Okay, and then we put it there. So delta H, right? It's going to be that specifically. It's going to be always in the case for this. You need to put that. Let's try to, yes, the products, right? So it's going to be 2, open parenthesis, times what is the enthalpy for the products, in this case for sodium hydroxide. If you check for sodium hydroxide in the chart, you're going to find it, you're going to find it always like the liquid version, I'm sorry, the solid, but this is aqueous. So aqueous is another one you will need to search on the internet. If you search it, you're going to find that it is minus 470.09 kilojoules per mole, because when in solution, it releases more heat. If you put some sodium hydroxide into the water, it releases heat, right? So it touches your stir, so it releases heat. That's why it's 470. It's a little bit bigger to the other constant, like when being solid. And after that, and that plus, right, the one for hydrogen, which is 0 because in the products, and then you close square brackets, and then you will need to work with the other one. And all of that minus the one for the products. The one for the products, again, square bracket, 2 times, in the case with this, 2 times the enthalpy for sodium, since it's an element, a pure element, you put 0, right? And then you close parentheses, and that plus the one for water. So 2 times water in the liquid state, according to, if you check into the chart, you're going to see that it's 200 minus 285.8 kilojoules per mole. So you close the parentheses, close square brackets, and then you find equals. You're going to see that basically the enthalpy of formation for that specific reaction. If you inserted those values into the calculator, you use that part. It's just pretty simple. You insert all of them, is going to give you a value of minus 368.58 kilojoules in total, right? Kilojoules per mole. Okay, now that you have that one, since it's done, okay, and basically it's just right, the inserted part. Okay, now let's continue. Once you have that specific, so then you're going to, you will have to basically need to, yeah, I need to close this, and then that's it, exactly. So since it says they all, you've got already the answer, so you pass that value to the reaction, you copy it as it says, minus 368.58 kilojoules, right? Kilojoules over mole. Good. Now that you have that, okay, since you solved that, it's pretty easy. Put it over mole, and it's done. Now let's find the other one for the change of energy. For doing so, which is the class for today, I need you to just take into consideration the following formula, right? This formula specifically, the one that we did the previous class for talking about the amount of heat, which came from an interesting formula being said this one, right? I want you to remember this. Okay, so that formula we obtained it from heat, right? Heat plus work and stuff. So that as you can see in this moment, the total change of the total energy there, right? Right, wasn't here. This was Q, and this was work. And then you rearrange the formula. So we have this in terms for enthalpy. Now we're going to put it back as it used to be before for having this, like the total energy equals, and so on, so on, so on. The heat plus the work. How are you going to do so? So just remember that you're just going to move that formula to the original state or stuff. And let's try that again. So we go there. We have to write this, right? Symbol there, copy, yes, and stuff. Now, let's type. You're going to have this specifically. So if you want to know the change of energy, delta energy is going to be equals specifically to what? To the amount of heat, as it says, right, of enthalpy, which we already calculated, minus, right, pressure, right, and the volume. And remember, if I told you before that whenever this happens and stuff, and we have that specific formula, and that formula comes from something which is really similar to what we used to do before. So if you think about this formula, so this is pretty similar to something we used to do before. So since we're talking about gases, and this applies only to gases because gases exert work against the surroundings or against the universe, well, I am going to enclose something for you. You can see it. So all of this specific part is talking about gases, okay? That specific part is for talking about gases. So think about that. Put this there. So this is for gases. Okay, so then you're going to remember something really interesting about that. Because if you remember this amazing formula, the general formula for gases, Vp equals, right, nRT. So then you're going to remember the volume, pressure, number of moles, the constant, and temperature. Oh, so being said that, then you can replace basically all of this instead of BP in here because it's pressure and volume. So you can replace and we can put that in here. So then we can talk about the number of moles and the constant for gases and stuff. Being said that, so I need you to remember that for the gas laws we studied, we said that R is equals to 0.082, right? It was liters, if you remember, it was liters times atmosphere, right? And all of that was over mole times Kelvin, if you remember that, right? If you recall that part, so just line in a line there, we're making it into a fraction. If you understand that, then I'm going to pass it to conversion factors, because in this case, that constant, it is in this case, must give us something about in terms per joules. So let's pass it to joules. We use a conversion factor, right? And what I'm going to do, just change dr, but to a number which contains joules there. So as I told you before, if you remember that, if you recall that, I told you that in also previous class, I told you that 1 liter, right? 1 liter times atmosphere, right? Equals, specifically, I gave you a number, 100, right? On 1.32 joules. So that's a conversion that's normally that exists. You can search it on the internet. So we're going to use that conversion. So you put in the lowercase 1 liter, right? 1 liter times atmosphere, which is what I have in the upper part, is specifically 101.32 joules. And now that I have it in that converted to joules, then you just cancel, right? Cancel this one, liters times atmosphere, and then you're going to have a new constant, but now in terms per joules, which is going to be it's going to be 8.31 joules, right? And all of that over specifically mole times Kelvin. Got it? So I advise you always, whenever you're watching this video, you're pausing and going and watching it again and stuff. So you're going to have that part. That's the new constant for R. That's the new R for this equation specifically. So now let's change everything. Let's change this equation again. So if we put that there again, so then my new one is going to be energy is going to be equals, again, it's going to be delta H, which I already have calculated, minus 1. In this case, now, instead of PV, I'm going to put N, R, and T. As you can see, the number of moles, the R are just calculated, and the T. And if you pay attention, the number of moles is in moles, and the R is now in joules over mole times Kelvin, and the temperature is going to be in Kelvin. So if you cancel all of that, you can have the answer only in Kelvins, and I'm sorry, in joules. Being said that, since it's just in joules, make sure you transform that or divide to 1,000 in order you get to kilojoules, because the enthalpy was in kilojoules, okay? Now that we have that, now we have this new equation and stuff like that. How do you apply that new equation? I have solved this exercise in here into my notes for explaining this into a better way. So for doing so, what you're going to do now is that just insert into values. Since this part of the equation is talking about gases only, what you're going to do is just take notes, because now this N is the variation of moles, the change of moles from the end to the beginning. The R, you have it, and the temperature, obviously, if it doesn't say in the reaction to calculate that, we're going to assume it was at room temperature, unless it says the opposite. So let's get to work. If you put that part, you can do it into this way. You put this, it says the change of energy is going to be equals to the enthalpy, as it say, and the enthalpy we just calculated, well, in the beginning was minus 368.58 kilojoules. I'm going to go with kilojoules, all of that over mole, right? Over mole, and I will draw the line for fraction at the end, and now it says minus, and then open parentheses. That's the change of the number of moles for the gases. Let's analyze the equation. You have 1 mole of gas at the end. This is not a gas, so we don't count this one. It says 1 mole minus the number of moles of gases from the beginning. Liquid, water is liquid, so you have a gas. Sodium is not a gas, so definitely is 1 from the product minus 0 moles from the reactants. So no, that's the number of moles I'm just replacing. And all of that times R. In this case is the general constant for gases in terms per joules. So we'll copy that 8.31 joules, right? Joules over mole times Kelvin, right? Over mole times Kelvin. But also I will have to open a conversion factor, because, well, let's write fraction in here, and I will have to open a conversion factor because I need to convert that to kilojoules, because this one is in kilojoules. Got it? So then I know that 1 kilojoule, right, is exactly 1,000 joules, right? So now you use the conversion factor, and definitely it's going to be, now it has been converted into specifically the constant passed to kilojoules. If you do so, then again, we close parentheses till this point, and then we continue. What else is there? We have now the number of moles, all of that is the R, and all of that times the temperature. The temperature in this case, since it doesn't say what we are going to assume is the temperature at room conditions, so it's 25 Celsius degrees. You must pass it, as always in gases, to Kelvin. So 25 plus 273 is going to be, 25 plus 273 is going to give you 298 Kelvin, which is the temperature in Kelvin, right, for a room condition. So once again, I am going to type this for you to get it. And to this point, this is the number of moles, right? This is the number of moles. This other one, all of that is the R for constant, and the last one is the temperature. I just replaced those values. And then if you continue working there, you continue where type in this, we're going to have that at the end, the total energy is going to be equals to minus 368.58 kilojoules over mole, so on, so on, so on, right? And we continue that, and all of that minus, right? All of that calculation is going to give us, let's type 1 minus 0 is 1 times 8.31 times 298 and divided to 1,000. Yeah, it's going to give you specifically 2.47 kilojoules again over mole. Got it? And so definitely that is going to be over mole. So what is that? If you pay attention to this part specifically, that this value, not this value. Okay, so in the first place, this value is the one for the heat evolved for the reaction, and this value is the work, right? Sort of the work done for the reaction. And yes, there was some work, as you can see, some hydrogen gas released to the surroundings. So that's the small value, but there's some exerted value there. And at the end, so what you need to do is add the two values to find the total energy change, the total energy change. So if you do so, basically it's done. You just add the two of those values, and you're going to have exactly 300, it's minus because it's exothermic, 371.06 kilojoules over mole. Oh, wait. Yes. Oh. At the end, the total energy change, as I said, equals to minus 371.06 kilojoules over mole. Okay. Being said that, Mejines, so that was it what I wanted you to do. So in here, oh, sorry, and here there was minus, so forget about that value, and that's it. Okay, so please take notes about this process and stuff. I just wanted to have this equation, take into account all of what we did today and understand everything, so you go back to the video and stuff. Okay, a pleasure, Mejines. So that was it.